Hello my precious friends, I really hope that you are doing great. Welcome to our today's class. It is our fifth lesson on the seventh topic of Form 3 work, which is called Electrostatics 2. As usual, let me comment by giving the quote of the day, which states that no dream is impossible in the presence of effort, desire and attitude. We shall discuss that quote at the end of our class today. So today we are looking at the factors affecting the capacitance of a parallel plate capacitor. So the first factor is what we call the area of overlap of the plates. So a point to note, when we talk of the area of overlap of the plates, we simply mean the area of one of the plates. For example, if our positively charged plate of the capacitor has an area of 2 square meter, then the negatively charged capacitor or plate of the capacitor also has an area of 2 square meter, then the area of overlap of the plates will just be the area of one of the plates. For example, in this case, the area of overlap between these two plates is actually 2 square meters. So you just take the area of one of the plates will be equal to the area of overlap between the two plates. For example, don't take, for example, the area of overlap as maybe 2 plus 2, which will be 4 square meter. No. When we talk of the area of overlap, will just be equal to the area of one of the plates, not the area for both plates. So in this case, the area of overlap is strictly 2 square meter. So we are saying that the first factor that affects the capacitance of a parallel plate capacitor is the area of overlap of the plates. Then remember that we defined the capacitance of a capacitor as simply a measure of the amount of charge the capacitor can store when connected to a given voltage. So if the capacitance of the capacitor is a measure of the voltage or the charge that particular capacitor can store, then it simply means that if the areas are large, then it means that capacitor has the ability to store a lot of charge. Therefore, and the amount of charge stored, that is simply the capacitance of that particular capacitor. So it means the larger the area of overlap, the more the capacitance or the more the charges that can be stored. Therefore, we are saying that the capacitance is directly proportional to the area of overlap of the plates. So this one simply means the larger the area of overlap of the plates, the more the capacitance it can store, because the capacitance is just the amount of charge. So you can see even for this particular plate, for example, here we have 1, 2, 3, 4, 5, 6 charges. Obviously, if you had a larger, that is plates of a larger area of overlap, for example, if the plate was larger, if it had maybe an area of 7 square meter, we expect it to have the ability to store more charges, because an area of 2 square meter is storing charges of 1, 2, 3, 4, 5, 6 charges. So obviously an area of 7 square meter will store more charges. Therefore, the larger the area of overlap, the more the capacitance or the more the charge that a given capacitor can store. And obviously the smaller the area of overlap, also the lesser the capacitance or the lesser the charges of that particular capacitor can store. Therefore, if two quantities are such in a way that if one increases the other, then if one decreases, it also decreases the second quantity, then we say such quantities are directly proportional to one another. Therefore, capacitance is directly proportional to the area of overlap of the plates. So mathematically, capacitance C is, so this the direct proportionality simple, is direct proportional to the area A. So this A represents the area of overlap. Remember, we have said that the area of overlap is just the area of one of the plates. So this forms our first equation. Then the second factor that affects the capacitance of a parallel plate capacitor is what we call the distance of separation between the two plates. Yeah, to understand this better, just like for the magnets, remember, if the poles of a magnet are closer to each other, that is when the magnetic forces are strong. Then if the poles of a magnet are far away from each other, then the magnetic force will also be very, very small. For example, you can just take a magnet with maybe a nail or any magnetic material. If you bring that particular nail close to the poles of a magnet, the force of magnetism will be very high. But if you take the nail far away from the magnet, then the magnetic force will be very, very weak. So the same thing happens to capacitors. So if the plates are closer to one another, that is, if the positive plate of the capacitor and the negative plate of the capacitor are very close to one another, it means that the capacitance will be very high. That is, the amount of charge that that particular capacitor can store will be very, very high. Because remember, the two plates of capacitors are usually have different charges, or they are charged oppositely. So if one of the plates is charged positively and the other plate is charged negatively, we know that unlike charges will always attract each other. And of course, the larger the attraction, the more the capacitance, or the more the charge that that particular capacitor can actually store. Therefore, the smaller the distance of separation between the plates of the capacitors, the more the charge, or the more the capacitance, or those particular plates can store. And of course, if you increase the distance of separation between the plates, just like in magnets, whereby the magnetic force becomes very weak, also if you increase the distance of separation between the plates, it means the force of attraction between the positive and the negative charges will be very weak, hence less capacitance will also be stored, or less charges will actually be stored. Remember, the attractive forces between the negative and the positive charges is what keeps the charges closer to one another, or is what ensures that the plates of the capacitor have a lot of capacitance, or they have more charges which are closer to one another. Therefore, in short, we are saying that the distance of separation between the plates is inversely proportional to the capacitance. That is to mean, the shorter or the smaller the distance of separation, the more the capacitance, because the shorter the distance of separation between the plates, actually the more the attractive forces between these particular charges on the plates of the capacitor. So capacitance is inversely proportional to the distance of separation between the plates. So the shorter the distance, or the closer the plates of the capacitors are, the more the capacitance, or the more the charge that that particular capacitor can actually store. But the larger the distance of separation between the plates, the fewer the charges that that particular capacitor can store, or the smaller the capacitance. Therefore, capacitance and the distance of separation between the plates are inversely proportional to one another. So this is the proportionality, simple. Then if quantities are inverse, we simply take 1 over that particular quantity. So remember, you can be asked a question in a very unique format here. For example, someone can tell you to state any two adjustments that can be made to a parallel plate capacitor to ensure that the capacitance increases, or the amount of charge that it stores increases. So the adjustments that you can make to the plates of a capacitor to ensure that it stores more capacitance, the first adjustment will be to increase the area of overlap of the plates, because the larger the area of overlap, the more the capacitance. The other adjustment you can make is to reduce the distance of separation between the plates, because the smaller the distance of separation, the more the capacitance. Another person can ask you to state any adjustments that can be done to a parallel plate capacitor to ensure that it stores less charge or less capacitance. So in order for it to store less capacitance, the adjustments that you'll make, one will be to reduce the area of overlap of the plates. Then the other adjustment that you can make to reduce the capacitance that a given capacitor will store is to increase the distance of separation between the plates of that particular capacitance. So remember, this is our second equation. So I want to combine equation 1 and 2. So if I combine equation 1 and 2, I'll have the following. So remember, C is common, that is capacitance is common for both equation 1 and 2. Therefore, I'll just use 1C to represent both. Then if I have C is direct proportional to A, at the same time C is inversely proportional to the separation distance D, it simply means when I combine these two, I'll simply multiply A and 1 over D. Therefore, the capacitance C is directly proportional to A, just like in our first equation, but at the same time it is inversely proportional to D. So you just multiply the A and the 1 over D, because we have combined C, because after all C is just the same. It's just like we are substituting actually C in the other equation. So C is directly proportional to A, but at the same time it is inversely proportional to D. So if I compute this, A times 1, I'll simply obtain A. Therefore, capacitance is directly proportional to A, but it is inversely proportional to the distance of separation. Remember, to remove the proportionality symbol, we simply introduce equal signs with a constant. Therefore, C will be equal to, so the proportionality symbol is represented by equal signs with a constant. So C will be equal to equal sign, a constant times A over D. Then the constant in this case, we call it the epsilon, or the constant is simply called the permittivity of the insulating material. So remember, the insulating material is just the material that is separating the plates of the capacitors. Just that is, in our previous class, we did say that the plates of the capacitor are usually separated by a medium, which is does not allow the flow of charges. Examples of medium, we gave glass, we gave paper, we also gave vacuum as an insulating material. We also talked of air. So C will therefore be equal to, that is capacitance will be equal to the epsilon multiplied by the area of overlap between the plates divided by the distance of separation between the plates, where this symbol is called epsilon. So it is just a Greek letter which is called epsilon. So remember, in Greek, just like where we have the alphabet, that is A, B, C up to Z, in Greek they also have their own alphabets. Actually, the first alphabet in Greek is called the alpha, the second alphabet is beta, the third is gamma, the fourth is delta, the fifth is epsilon. Then their last letter on the alphabet is what we call the omega. That is, omega corresponds to Z, that is in our alphabet. Then alpha corresponds to letter A. So that's why you will hear some musicians singing that you are my alpha and omega. That is the start and the end. So alpha is the first letter which corresponds to our letter A. Then omega is the last letter which corresponds to our letter Z. So let me just give you the first 5 letters of that is alphabet in Greek. So the first letter, which is A, is called the alpha. Letter B is called beta. Letter C is called gamma. Letter D is called delta. Then letter E is called epsilon. Now the one that we are using here. So actually epsilon is the 5th letter in the Greek alphabet. So we pronounce it as epsilon. So it is just a constant which that is dependent on the medium between the plates. So that means the epsilon, actually the value of epsilon will depend with the material that we have used to separate the plates of a capacitor. So the epsilon can actually change. So it is dependent on the material medium between the plates, and it is called the permittivity of the insulating material. So if the plates are in vacuum, that is, if the separating material between these particular plates of a parallel plate capacitor is vacuum. Remember, vacuum is just a place without air. So if the plates are in a vacuum, or when the dielectric is a vacuum, then the constant, we call it the permittivity of free space, which is noted by epsilon naught. So this is epsilon, then the 0, which is a subscript, we call it the naught. So this is the epsilon, it is pronounced as epsilon naught. So this is the symbol for the epsilon naught. So the permittivity for free space is usually a constant because it is not varying. We are talking of a vacuum. So the permittivity of free space, which is epsilon naught, is given by 8.85 times 10 power negative 12 farad per meter. Remember, applying the laws of indices, we can rewrite this one as 8.85 times 10 power negative 12 farad meter power negative 1. That is courtesy of the laws of indices. Therefore, if I rewrite this formula, substituting my epsilon with epsilon naught, that is, if the material that is separating the plates is actually a vacuum, then in that case it means we shall have the following. So thus C will simply be equal to, so for the epsilon we are using permittivity of free space, which is epsilon naught, then times the area of separation, that is the area of overlap between the plates, divided by the distance of separation between the plates. Of course, where epsilon naught is just the permittivity of free space, which is 8.85 times 10 power negative 12 farad per meter. So I want to show you how we are arriving at the units of farad per meter. So from this equation, if I make epsilon naught subject of the formula, I'll simply multiply both sides of this equation by the reciprocal of A over D. So epsilon naught will simply be equal to D over A times C. That is, I'm multiplying both sides of this equation by the reciprocal of A over D, so that I just remain with epsilon alone. So epsilon alone will simply be equal to D over A multiplied by C. That is, I've just multiplied both sides by the reciprocal of A over D, which is actually D over A. So from this equation, if I just consider the units alone, So remember, D is the separation distance. The units for distance, which is a length, is just the meters. Then A is the area of overlap. The units for area, of course, is the square meter. Then C is capacitance, which is measured in farad, that is F. So if I divide both sides, so remember M, that is meters, will divide with meter squared, so that meters into meter 1, then meters into meter squared, I'll just get meter. So the units will remain as meters, that is farad per meter. So farad divided by the meter, which is just farad per meter, or farad meter power -1. That's why you are seeing us, we are having the units of farad per meter for the epsilon naught, or for the permittivity of free space in this particular case. Yeah, so that is what you need to know as far as the factors affecting capacitance of a parallel plate capacitor are concerned. I can just give you some more letters. You can also investigate the letters in the Greek. So the first letter A was alpha, the second is beta, the third is gamma, the fourth is delta, the fifth is epsilon, the sixth is the zeta. Then we have the last letter, which was the omega, which corresponds to letter Z in our own alphabet. Next, lastly, let's look at an example involving application of the formulas that we have just derived. So the question reads, two plates of a parallel plate capacitor are 0.6 millimeters apart, and each has an area of 4 square centimeters. Given that the potential, that is the potential difference between the plates, is 100 volts, calculate the charge stored in the capacitor. So in order to calculate the charge, we showed earlier that charge is equals to the capacitance times the potential difference, that is the voltage. So our first aim is to find the capacitance, then after that we just multiply by the voltage in order to get the charge. So our first task is to look at the values that we are given so that they can help us to find the capacitance. So we are told that two plates of a parallel plate capacitor are 0.6 millimeters apart. So if the plates are 0.6 millimeters apart, it means that 0.6 millimeters is the distance of separation between the plates. Therefore, the distance of separation D is 0.6 millimeters. Then we know the SI unit for length is meters. Therefore, I'll convert the millimeters into meters. So we know that from MCD, MDHK, we know that 1,000 millimeters is equals to 1 meter. What about 0.6 millimeters? So that will be 0.6 over 1,000 millimeters times 1 meter, which gives us 0.0006 meters. The next, we are given each has an area of 4 centimeters square. Remember, we said that the area of one of the plates is equals to the area of overlap between the plates. Therefore, the area of overlap between the plates is just the area of one of the plates. So because we are told that each plate has an area of 4 square centimeters, the area of overlap will just be equal to the area of one of the plates. Yeah, there are students who make a mistake of multiplying this area times 2. So just know that the area of overlap is equal to the area of one of the plates, but not the area of both the plates. Therefore, the area of overlap is 4 centimeters square. Again, we know the SI unit for area is square meter. And we know that 10,000 square centimeter is equals to 1 square meter. What about 4 square centimeters? So that will be 4 square centimeters over 10,000 square centimeters times 1 square meter, which gives us 0.0004 square meter. Then again, we are also given that the potential difference between the plates is 100 volts. So the first thing, you just highlight the values that you have so that you see which formula can suit them. So from the values that we have, remember we're also given the permittivity of free space, that is epsilon naught, which is 8.85 times 10 power negative 12 farad per meter. So we just find the capacitance C. So we have said that capacitance C is equals to epsilon naught, that is permittivity of free space, multiplied by the area of overlap between the plates divided by the distance of separation between the plates. So epsilon naught we are given as 8.85 times 10 power negative 12, that is farad per meter, multiplied by the area of separation, that is the area of overlap between the plates, is we have computed it as 0.004 square meter. Then divided by the distance of separation, we have it as 0.0006 meter. So if you compute these using your calculator, you will simply obtain 5.9 times 10 power negative 12 farad. Remember, those are the units for the capacitance, that is the farad. So once we have the capacitance, we can now easily calculate the charge stored, because charge is equals to CV. Remember, we said the easiest way of remembering it is just to say charge Q is equals to curriculum vitae, the curriculum vitae. CV, where C is the capacitance and V is the potential difference between the plates. So the capacitance, we have it as, from here, we have it as 5.9 times 10 power negative 12, of course, farad, multiplied by potential difference V, we are given as 100 volts. So 5.9 times 10 power negative 12 times 100, so the 100, we just move the decimal points backward 2 times, so that if it is negative 12, they will come back to negative 10. So the charge stored is actually 5.9 times 10 power negative 12 times 10 power negative 10, that is coulomb, because that is charge. Then lastly, I have an exercise here that I recommend you should try at your own free time to gauge your understanding of the concepts that you have just learned. Of course, if you have any challenges in any of the questions given in the assignment, feel free to drop a comment specifying the question that you need help in, and of course I'm here to help where possible. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that no dream is impossible in the presence of effort, desire, and attitude. So the quote is just reminding us that it is still possible to achieve our dreams. What we need to do is to first develop the desire and courage to overcome the fears that are still holding us back. Yeah, most of us have not started achieving, working towards their dream because they fear so many things. They fear that maybe they could fail. They fear other people's opinion. So you need first of all to have the courage and the desire to overcome the fears that are still holding you back. After overcoming the fears, what you need to do next is that we also need to develop a positive attitude towards our work ethic. Yeah, you cannot achieve your dream without putting in the work. And lastly, we must be willing to put in the effort that is needed in order to make our dreams to come true. And lastly, recall that just like in football, you don't have to give up at the first half. Instead, you need to concentrate on winning the second half. So similarly, you can just compare your life to football. The first half in this case represents the time when you are going through difficult moments. Then the second half represents the period after you have overcome the difficult moment. So the difficult moment is not supposed to make you give up. It's meant to give you the effort and to develop your character so that you can achieve, you can have the right mentality and the right character in order to match to your greatness. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you are new to the channel, kindly hit the subscription button and also turn on the notification bell so that whenever I upload a new video, you will get notified. If you know any student that you honestly think could benefit from this content, kindly refer them to Kind Tuition Academy or just share my link to them. This is Kind Tuition Academy. Until next time.